Given few discrete points over a function, we know that we can use Taylor series to find the derivative of the function. There is, however, an alternative. In fact, there are several alternatives, but we will talk about only one. That is, given few discrete points over a function, we can fit a polynomial over those discrete points, and then we can take the derivative of that polynomial analytically. The result will be just the same as the finite difference method. Let us see with some examples. Let's take a function ux, that is ax plus b, which means a straight line, given that a and b are constants. We know the derivative of that function u prime x is equal to a. If we want to find the numerical derivative of this function, we need to know u at x plus delta x, which is of course a multiplied by x plus delta x plus b. And similarly u x minus delta x, which is equal to a multiplied by x minus delta x plus b. Now, numerically speaking, the forward difference u prime x is u x plus delta x minus ux divided by delta x, which is given by a multiplied by x plus delta x plus b minus ax plus b divided by delta x, which is equal to a. You can see that this numerical derivative is same as the analytical derivative. Similarly, in backward difference, we have ux minus delta x divided by delta x, which is equal to ax plus b minus a into x minus delta x minus b divided by delta x. That's equal to a. And central difference, where u prime x equals u x plus delta x minus u x minus delta x divided by twice delta x, and the same is once again a. So we can see that the numerical derivative, forward difference, backward difference, central difference, all of them are same as the analytical derivative u prime x equal a. Let us take another function. Let us slightly complicate the function and take ax square plus bx plus c, keeping a, b, c to be constants. The analytical derivative is u prime x, that is twice ax plus b, and the numerical derivative will be obtained from ux plus delta x and ux minus delta x, which are given respectively as a x plus delta x square plus b x plus delta x plus c, and a x minus delta x square plus b x minus delta x plus c. Now you see, in forward difference we have u x plus delta x minus ux divided by delta x, and we have a x plus delta x square plus b x plus delta x plus c minus ax square plus bx plus c divided by delta x, which is twice ax plus b plus a delta x. So you can see that we do have a truncation error of the order of delta x. Exactly a delta x is the truncation error. This is a fast order accurate scheme. This is what we are expecting. Similarly, in backward difference, we have ux minus delta x divided by delta x, which gives us twice ax plus b minus a delta x. you can see that the derivatives obtained by forward difference and backward difference are different. One has plus a delta x, another has minus a delta x. None of them are same as the analytical derivative. Both of them have truncation error of the order of delta x. So both the schemes are first order accurate. That is what we are expecting. The analytical derivative twice ax plus b, and with that we have a truncation error of the order of delta x. Now we want to continue with the same function and see the central difference, that is ux plus delta x minus ux minus delta x by twice delta x. If I plug ax plus delta x square plus bx plus delta x plus c minus ax minus delta x square minus bx minus delta x minus c, then the central difference comes twice ax plus b, that is same as the analytical derivative. It does not have any truncation error as it was in forward and backward differences. We can continue with similar examples and we can take a cubic polynomial, that is ax cube plus bx square plus cx plus d. We can take that as u and we can try taking derivatives. It will get more and more complicated, but what you will see that all three schemes will then have non-zero truncation error. So you can think about it, what's going on, why now in linear none of them has truncation error, in quadratic central doesn't have truncation error, other two do have truncation errors, for cubic all of them have truncation error. So what's going on? Now before I answer this question, let's get back and check our fundamentals once again. Why do you actually need numerical differentiation? The examples we have just taken, we know the function and still we are doing numerical derivatives. These are completely unnecessary. These are for our practice only. When we know the function as an analytical expression, we don't need numerical derivative at all. If we know the function, we can simply differentiate it analytically. So when do we need numerical differentiation? Well, maybe the function is too complex that we cannot have an analytical derivative very easily. So we carry out a numerical differentiation, and for that, as complex the function as it is, we can take few discrete points of x, and for those x's we can get the values of u. So we can take the sets of values xi, ui. If we have several xi, ui, then we can carry out a numerical differentiation. That is case 1. Then case 2 is when we do not know the function ux at all, we have no idea about the function ux. Instead, we only know few values of u for certain values of x. Now, knowing only few discrete values and not the function, we certainly, if we need the derivative, we certainly have to take the numerical derivative. Then how can I take numerical derivative? To take this numerical derivative, knowing only few discrete points, what we do, we put a polynomial through those discrete points. If you have taken the course ME 685, you must have done polynomial interpolation. This is the same procedure here. That is fitting a polynomial exactly through those points. It is not a least square curve fitting. Please do not confuse with least square curve fitting. Least square curve fitting is knowing the equation of curve, we fit it through certain points approximately, keeping the error to be at minimum. But in polynomial interpolation, as many points as we have, we try to fit the highest order polynomial possible through those points. So here, what I am suggesting is that if we know only few discrete points of a function and we want to take derivative of that function numerically, what we do is that we fit a polynomial through those discrete points and then we simply analytically take the derivative. The expression that we will get that derivative, that will be same as the derivative we are getting through finite difference procedure. This is something very exciting now. And if we have more points, we should be able to fit higher and higher order polynomial. And fitting higher order polynomial is equivalent to getting derivatives using many more points, which means that we have already seen through our Taylor series analysis is that more points we have increased order of accuracy. So fitting higher order polynomial will give us higher order of accuracy. So to conclude, we can fit polynomial over discrete points and we can take the derivative, or we can take those discrete points and we expand them in Taylor series. From that we can evaluate derivative using the procedure that we have discussed in last few lectures. Let us take an example. Let us say that for a function u, I have three discrete points xi minus 1, ui minus 1, xi ui, xi plus 1, ui plus 1. Now we want to take a derivative at xi. So what we do, we have to fit a polynomial over this three discrete points. The simplest possible polynomial we can fit is ax plus b, that is a straight line. But for straight line, we don't need three discrete points, we just need any two. So we can pick any two and fit a straight line. If we indeed fit a straight line ax plus b, then my derivative is simply a, and we know that ui is axi plus b, ui minus 1 is axi minus 1 plus b. Using these two equations, we can find a and b. In fact, we don't need b at all, we need only a to get the derivative. You get the a from these two equations. If you solve these two equations, then your a is ui minus ui minus 1 divided by xi minus xi minus 1. And we already know that this is exactly the definition of numerical derivative using backward difference. Similarly, if we fit a straight line between ui and ui plus 1, then my ui becomes axi plus b, ui plus 1 becomes axi plus 1 plus b. If we solve these two equations and find a, we have a equals ui plus 1 minus ui divided by xi plus 1 minus xi, which is exactly equal to the forward difference expression of numerical derivative. Finally, if we use ui minus 1 and ui plus 1, then again we have ui minus 1 equals axi minus 1 plus b, ui plus 1 equals axi plus 1 plus b. We can solve these two equations to find a, and my a is ui plus 1 minus ui minus 1 divided by xi plus 1 minus xi minus 1, and this is exactly the central difference expression for u prime I. So you can see this 2-point backward difference, forward difference or central difference are nothing but fitting of straight line on 2 points over the function and then differentiating that straight line. To understand this procedure better, you can fit a polynomial ax square plus bx plus c with these 3 points. Its derivative is twice ax plus b, and since the polynomial is passing through these 3 points, we have ui minus 1 equals axi minus 1 square plus bxi minus 1 plus c. ui equals axi square plus bxi plus c. ui plus 1 equals axi plus 1 square plus bxi plus 1 plus c. We have 3 points, so best we can have is ax square plus bx plus c. We cannot use any higher order polynomial because here we have to find out a, b and c. We need 3 equations, so we need 3 points. So using these 3 equations, you can evaluate a, b and c. In fact, we don't need c, only a and b should be sufficient because my derivative involves only a and b. So you solve these 3 equations, find the expression for a and b, and see if the expression of ui prime matches with the same from the finite difference. It should match. The overall calculation here is slightly complicated. So what I suggest that you use an uniform grid, that is xi minus xi minus 1 equals xi plus 1 minus xi equals delta x. This will be a very useful exercise, and use of polynomial for finding numerical derivatives are certainly not as simple as the use of Taylor series, but this idea can give us a lot of insight in numerical differentiation, especially if you use higher order differentiations. Thank you. That's all for this lecture. I'll see you in next class.